I'm going to be talking more about probability than statistics this time, and of course Ron said that probability is a little bit easier to understand than statistics. So let's see how that plays out. So let me share my screen here. So hold on a second. Share this one here. So I've been working on TamStat, which stands for Taming Statistics, for quite a while. And one of the nice features that I found is the probability operator, which allows us to calculate probabilities from many of these distributions that Ron was talking about. A little bit easier than using them in statistics. So I want to talk a little bit about how I've extended that domain to do some additional things. I use this as a tool when I teach statistics as a learning tool. So some of the statistics might seem fairly simple, but I've taken advantage of all the functions in APL which can be applied to this operator. So in general, statistics deals with 4 families of functions. And the first one would be what we call summary functions or descriptive statistics. So things like the mean and the standard deviation and things like that. Probability distributions, and these are more theoretical models, and Ron talked about a few of those, are another type of function that we use in statistics. Relations. We often talk about relations such as less than or greater than or equal to, and of course we have these functions in Dyalog APL. And the fourth type are logical functions. And this is the one I'm going to talk about because up to now, I had not yet incorporated logical functions into TamStat. So we're going to, the latest TamStat version incorporates logical functions. So I want to talk a little bit about them before I show how they're used in TamStat. So logical functions basically have a domain of 0 and 1 and a range also of 0 and 1. And not is the simplest one. You just 0 to 1 or 1 to 0. But we also have and, or, and we also have NAND, not and not or. And these all take zeros and ones as inputs, and they return 0 and 1 as outputs. Now, in addition to these basic logical functions in Dyalog APL, we can apply relational functions. We can apply them. We can take relational functions and apply them to Booleans. And these become simple logical functions if we restrict the domain of these relational functions. And so we can have if and only if equals. If A and B are both Booleans, then this becomes if and only if. Exclusive or is not equal. Relative complement is less than, without, greater than, implies, and if greater than and less than or equal to. So we can use these functions as well. We can treat them as logical functions when we restrict the domain to 0 and 1. Now I want to talk about the current probability operator that's out there right now, and it's and so if we wanted to calculate the probability that you get at least 3 heads in 7 fair coin tosses, if we were doing this in Excel, we would have to use the binom distribution, binom.dist, and we have to say 2 because we're talking at least 3. So you have to adjust it down by 1. And then you say 7 is the number of coin tosses, 0.5 is the probability of success, and 1 means it's cumulative. And then you have to take that whole thing and subtract it from 1. So it's a little bit involved. In R, kind of similar, you say P binom, and then you have to also use 2. And you have to say lower tail is false. And so I thought this was a little clumsy. So in APL TamStat, of course, we can say P is assigned 7.05. These are the parameters, binomial probability greater than or equal to 3. Kind of reads fairly English-like. But this fits in very nicely with Dyalog APL syntax, because we can make prob is the operator, the left operand is the distribution, the right operand is the relational function, and then the parameters become the left argument, and the right argument is the number 3, which is what we're interested in. And of course, we can type enter P and get our probability, which is 0.77% of the time we will get at least 3,007 pair of coin tosses. So that's the current probability operator syntax. Now, I wanted to expand that because this is one way to talk about probabilities with regard to statistical distributions. It's more theoretical probability, but we can also calculate probabilities in many different ways. So I want to talk about the operands of the new probability operator in TamStat. So my key down here is functions are in blue, arrays are going to be in green, and the probability operator itself will be represented in orange. So I used some color coding here. So in the current method, we pair a relation with a distribution, and the current probability operator pairs those two operands together. And that was the current way that this is done. Now we can expand that. One way is to take a frequency distribution, and this is a way we can set up a custom distribution. It has to be a discrete distribution, and we can relate that this is a new way to do it. We can just treat the frequency distribution as the left operand without any parameters. Another way is we can take a contingency table is kind of like a frequency distribution, but with two different variables. And so we can take a contingency table and pair it with a logical function. So we're still going to use the probability operator, but we're going to pair it with a contingency. We're going to pair a contingency table with a logical function and calculate a probability that way. And I'll show some examples of that. We can also apply this logical function to just a frequency distribution where there's only one variable. In addition to that, we can use the independent function as an operand to the probability operator and calculate independent, when the two variables are independent of each other, we can also calculate probabilities. So you can see that there's a whole bunch of new syntaxes that will apply to the probability operator. So let's take a look at custom probabilities using a frequency distribution as left operand. So I have a variable called family, and I have a function called frequency, and I'm going to assign that to the result custom, which is basically just a matrix. The variable family, I asked students how many siblings they have. So they have, 2 of them had no siblings. They were an only child. 17 had 1 sibling, and 11 had 2, and so on. And I want to calculate probabilities from this table. So I can indicate custom probability equals to 1. So this is no longer, I've replaced a statistical distribution with this matrix. And so I get a 44%. And I can do cumulative probability, custom probability less than or equal to 1, upper tail probabilities, interval probabilities, probability between 1 and 4 siblings. What's the probability here? They have at least or more than 2 siblings, and so on. So that's the first way we've enhanced the probability operator. So the extended syntax of the probability operator, this is the current syntax that we have, where we have parameters on the left and we have the value on the right. And then these are the operand can be a distribution or a table that I indicated, and the relation is the right operand. The extended syntax, we're going to put in a logical function that pair a logical function with a table, and the events will be the operands, will be the left and right arguments, sorry. We can also, instead of a table, we can just use the variables themselves, or we can pair the logical function with the independent function as the right operand. And so table is a matrix containing integers or probabilities between 0 and 1. Variable is a nested vector or a character matrix. And in all cases, the result is going to be a probability, some number between 0 and 1. So basically in my classes, I discussed these are the very basic rules of probability: the complement rule, the intersection rule, or what we often call the multiplication rule, the union, which is the addition rule, and conditional probability. So I'm going to talk about these basic types of probability and how we can implement them using the probability operator. So I won't go into details, but these are, if you've had a basic probability course, you should be familiar with some of these formulas here. So the basic rules of probability we have. Let's create a contingency table. So I have a data set, and I have a variable called sex and a variable called party. And so CT is now a matrix, and basically sex will be female and male, and party would be Democrat, Independent, and Republican. And so I did a survey of my students, and so 3 students were Democrats and female, and so on. So this is called a contingency table. So we're going to take that and make that the right operand of the probability operator. So I say prob CT, and this is not, so this is a monadic form. So I can say, what's the probability that a random student is a Democrat, who is not a Democrat, sorry. So that's not. So we would simply take the 3, we would simply get the total and then find out, what's the probability that a student is not a Democrat. So that would be about 71%, okay? Because 11 out of, I think there's a total of 38. 11 out of 38 would be Democrats, so 1 minus that would be 0.71. What's the probability the student is a Democrat and female? So that would be 3 out of the total of 38, and that would be about 7.078. So you can see the left operand is and the right operand is the contingency table. Or what's the probability that the student is Democrat or female, and we get using this operand. Now we don't have to take one from the row and one from the column. I can also take what's the probability that the student is a Democrat or independent. So we can take, as long as these headings are unique, the first row and the first column part, those headings are unique, we can do that. So I get 57% of either Democrat or independent. And if I say Democrat and independent, that can't be true. They can't be both. So that would be 0. So these are the basic rules of probability. Now we can do some exotic examples by using some of the other functions that are rarely used functions in Dyalog APL. So here's our contingency table again. So supposing I have a male, or what's the probability that I have a male or Republican? Okay, that's the probability that a student is male or Republican. But what's the probability that a student is not male or Republican? So this is a more complex one. Well, I can put in not or as the operand. as a left operand and get out that particular value. What's the probability that a student is male or Republican, but not both? So I can use exclusive or, which is not equals, and I can get that. Okay. In addition to that, we have to deal with conditional probability, which is a slightly different flavor. What's the probability when one of the conditions is known? We can condition probability based on what we already know. So we can say, first of all, when we talk about conditional probability, we have some concepts. Marginal probability is when we only deal with one of the variables. So what's the probability that a student is a Democrat? So I can say probability, the right operand, of course, is the matrix, and the right argument is D. And then if I want the right, I want just D. I don't care what's on the left. I can just use right tack in order to get the probability the student is a Democrat, which is 11 out of 38. So that's what we call marginal probability. I can do the same thing for the other variable, sex. I can say, what's the probability that a student is female? Again, using the right tack. Joint probability, of course, is just and. So Democrat and female. And so if we take joint probability and divide by marginal probability, we get conditional probability. So conditional probability is the probability of A given B. So I would say, what's the probability of a student as a Democrat, given that we know that the student is female? And so that would be about 0.333, which is this joint probability divided by this probability here. And of course, the converse is going to give you a different answer. What's the probability the student is female given that the student is Democrat? And I'm using vertical bar because that's the symbol that we use when we teach probability. That means given that. But here it's the absolute value function, but I used it because it kind of matches nicely with the conditional probability. Now, some people prefer using set theoretical notation. So instead of saying A and B, they like to say, what's the intersection of A and B? If A and B are events, okay? And so you can use intersection and union, and also without. So if you prefer using these symbols, instead of saying and probability, you can just use intersection, get the same result, or union. And greater than, which might be confusing to some people, they might prefer to use without. That's the probability that a student is female but not Republican. If we have two variables that are independent of each other, the calculations are simpler. Basically, what's going on, if two events are independent, if the occurrence of one has no effect on the occurrence of the other. So in particular, the probability of A intersect B, or probability of A and B both being true, is simply the product of the individual probabilities. To find the probability of two independent events requires only the individual marginal probabilities, probability of each of the individual events. So for example, the probability of A or B, if they're independent, is simply the probability of A plus the probability of B minus the probability of their product. If they're not independent, it's more complicated. So if, in the case of independence, we can use the probability operator in a slightly different way. So we're going to use the independent operand, or IND for short. So the probability, if I have a deck of cards and I select an ace, what's the probability that I select an ace? So we're going to call the event A. So that's simply 4. There are 4 out of 52 cards are aces. So the probability of an ace is 0.0769. The probability that I select a black card, which is a spade or a club, is 26 out of 52, of course, 50%. Okay. now I can use, instead of using the names of the events, I can simply use the probabilities of the events with the independent operand in order to get out probabilities. So let's take a look. What's the probability that I get a black ace? Well, that's simply A represents the probability of an ace. B represents the probability of a black card. So A and prob, the left operand is and. The right operand says independent. So I don't need a table. All I need are the probabilities. So end will replace the table. And I have A and B. So it's simply going to multiply the two numbers together to get 0.38461, which I could have just said A times B, obviously. But we can also, what's the probability that I have an ace or a black card? What's the probability I draw a card that's either ace or black? These are independent events. Okay, the probability that a card is an ace has nothing to do with whether it's black. So I can just replace and with or, and now calculate the probability of that. What's the probability that the card is neither an ace nor black? Well, I can use any of the other operands like not or, and so on. So that's how that works. Okay. All right. Now I want to do a. This is all basically. I'm just showing you a demo. I want to do a live demo. I want to show you some work that I have been working on with TamStat and with Michael Bass, who helped me with some of the graphics. Because a lot of this, as a learning tool, I'd like to show you some graphics. So I'm going to, let me end the show here. And I want to put, I have a, TamStat session up. And so we're going to use the probability operator. So I'm going to select probability and probability wizard. Okay, so the wizard will come up in a minute. So you should now be able to see the probability wizard on your screen. So I'm going to select, I have a database, so I'm going to select, we'll just do the same thing. We'll select sex as the rows and party as the columns. And notice that it populates this little grid over to the right. And if you wanted to, you could actually put in your own summary data and calculate probabilities directly from this. But I just did this to save some time because I don't want to waste time typing in some numbers. But now we can calculate all kinds of probabilities from this simple table here. So for example, what's the probability for set A? There's a little drop down and it selects all of the headings like female, male, Democrat, Independent, Republican. And then here you have the conjunction, which can be any one of these APL symbols, and or conditional, right tack, left tack, not equals, equals, and so on. If you don't know what the symbols mean, we optionally have a section here that allows you to select it by name. So you can either select it by symbol or by name, and do it that way. The right operand is going to be the table, and then set B again is just another drop down. So female and Democrat. And so now we have a little Venn diagram down here, so you can take a look at that. And this shows you the probability that a student is female and a Democrat is 7.89%, which is the green area. Okay. Now, if we replace that with or, notice that or means it's either one. It's female or Democrat or both. And we give you the not only we not only give you the probability of what you're looking for, but also the probability of the complement. The complement is in gray. And we can do, if we want to do conditional, this gives an illustration of what conditional probability is all about. We have to restrict ourselves. What's the probability that a student is female, given that the student is a Democrat? And of course, we have to restrict ourselves to Democrats. So this gray area is the whole set, and then the area we're interested in is this green area as a proportion of the total area here. So I can do that. And of course, we can also put in some of the more exotic conjunctions, such as not or not equal, and it shades in the appropriate area that we're calculating a probability for. So exclusive or says the person can be female or Democrat, but not both, which is female and Democrat. So we have all kinds of things to do. Okay, if we select, let's select female and let's select Democrat and independent, for example, or Democrat or independent. And notice in this case, person cannot be both independent and Democrat. And so normally OR would shade in all three areas, but there's an X in there indicating that since Democrat and independent are in separate columns, they're not, and there's the probability that one could be both is 0, it puts in an X and it indicates that independent and Democrats are mutually exclusive categories. So that's how that works. And then finally, if we wanted to calculate independent probabilities, you can replace table with a little drop down with independent. Okay. And then what it does is it sets up two categories here. So set A, let's say that's the ace. The probability of an ace is turned out to be 0.03846. And I'm sorry, it was 0.07. Sorry, it was 0.077. I think it was about 0.077. And set B, probability that card is a black card is 0.05. And so it will calculate what's the probability that we have a black card, or let's try and what's the probability that the card is a black or an ace. And so it will calculate the independent probabilities, indicating that they are independent. Okay, and then it puts in the individual probabilities up here. And of course, we can put in any type of example that we want, not equal or equal if and only if. What's the probability? And all of these probabilities work with independent categories as well. Okay, so that's all I have. I think I'm just about out of time, so I guess I can take questions.
Yep, thanks, Steve. So one comment we got was, what a great learning tool.
Okay.
And the other one is along the same lines, and the person would like to use TamStat. Is TamStat open source? I'd be really interested to know how you do the calculation. I was trying similar things in ABL recently. Okay. So I guess TamStat is open source.
Yes.
We have a slight problem making it available because of some of the components used, but I think it should be possible to share a link to it with the conference material that will be made available.
Yeah. Okay.
Okay, and well, other than that, I think you've done it So great that nobody has other questions. They all understood it immediately. Compliments.
Okay.
Well done.
Okay. Well, thank you. Okay.